Welcome back to our video module on damped harmonic motion. Let's pick up where we left off. mx double dot plus bx plus kx equals 0. So get used to this. This type of thing we're going to see all the time. Now as I look at this, I see position, velocity, acceleration. All of these are going to combine together to go to 0. So I need something whose first derivative and second derivative are of similar form. You probably already know exactly what we're going to look at. We're going to say that x of t is equal to a e to the alpha t. We're going to say it's some exponential. Let's pretend it's an exponential and let's see what happens. Here we go. We'll plug in our numbers and see what we get. Let's see if that's x dot is a alpha e to the alpha t. X double dot is a alpha squared e to the alpha t. And I'm not saying what a or alpha is. They could be complex, they could be real, they could be combinations of numbers, they could be anything. Right now I'm just trying to find something that'll solve this equation or put it in the correct form. So what do we got? We got m a alpha squared, and just for kicks, e alpha t, I'm going to say that's equal to the triangle, some delta, plus b a alpha, and that's just because I want to save space, plus k a delta equals 0. I see in this that we have a e to the alpha t on all of these. So I know that these terms are going to have to meet some sort of quadratic with this function in here. So I can disregard it, and I get 0 equals m alpha squared plus b alpha plus k. Okay, so this is a quadratic. We know what alpha is. This will be our coefficient right here. Alpha equals negative b plus or minus square root b squared minus 4mk all over 2m. Great, so we have some sort of form for solving or for finding out exactly what this coefficient is up here. And this is really possibly the most important coefficient or the most important term in all of our damped harmonic motion, because we see something special happening here. We see that with underneath this radical, that b squared minus 4mk, that could be positive, in which case you have some sort of real solution. It could be a negative, in which case you have e to the negative, or e to some imaginary exponent, in which case you're going to have oscillations from Euler, or you're going to see this go to 0, in which case you're going to have a really simple solution. Now let's flesh this out a little bit more. Let's first pretend that it's real. So in that case, so if the term b squared is greater than 4mk, then we have a real term in here. And if that's the case, we're going to have an exponent, e to the alpha t. Well, what does that look like? That looks like our overdamped solution. So in our overdamped solution, take a look. We have e to the alpha t plus b e to the beta t. Now does that make sense? Overdamped. Overdamped is where the damping is really, really significant. So what do we see here? We see that the damping term is really big, and it's bigger than some sort of combination of the mass and the spring. We can't quite intuit our way there, but we can say that it does make sense at a very basic level. We see that we have a real exponent, we see that the b squared term is really high, and we expect basically an exponential behavior. The next one I want to look at is what happens if this term is complex. So in that case, it's b squared is less than 4mk. Now our e to the alpha t, that's going to be a complex exponent, which, as a quick reminder, that's going to be, remember, e to the I, we'll say alpha t equals cosine alpha t plus I sine alpha t from Euler. So right now we're looking at some sort of periodic function, which is what we would expect. B squared, this is less. That means the damping coefficient is going to be less than some sort of combination of the mass and the spring. Well, our original term, we had a damping which was 0, in which case you do see an oscillation. And we can go back up to the top and see that. That is our underdamped situation. So I wrote down critical balance here. I think what I meant was that the spring and the damping forces are balanced. What we say is we call it critical damping. I'll keep that balance in there because, I guess it is a balance of spring and damping forces, but we say it's critical damping. So you can infer right now, what is the critical damping? Well, that's when this term, B squared, equals 4mk. And in that term, we have an e to an alpha t, and from your recollection of 4th semester calculus, you're going to have an e to the alpha t, and you might have some other term, t e to the alpha t, and this should look familiar. We just saw it up here at the critical damping, where we have the function of time is the combination of two exponentials. And in this case, alpha really easily is negative b over 2m. So this is really actually what I find to be one of the more interesting solutions, because I see it as being just the perfect balance between spring and damping. So in summary, what we've seen is by introducing damping, we can create a more realistic model. And moreover, we can intuit our way to what some of these graphs might look like. This a little bit opens our eyes that when we finally use our mathematics, use our exponentials with our free body diagram and our equations of motion, we come up with a very interesting and kind of somewhat peculiar mathematical situation when we solve for our quadratic. That gives us 3 possibilities, and we can see that mathematically they're very significant, the difference between these 3. We have the overdamped, we have the underdamped, and we have the critically damped right here. Given our time situation, let's stop our video now and we'll pick up our train of thought on our next video.